Sure. In this Kaggle competitions, we like other projects, we were assigned the train and test and submissions. So our train, it was all the data, and our test was unlabeled data that doesn't have labels of the winner model A, winner model B, and winner type. And then we had also the submission format. So that was mostly focusing on the label that was missing in the test data, in addition to the ID for each label. So in the next slide, we will talk more about the details.
Yeah, so we were given a data frame with about 57,477 rows. So meaning like we have a unique ID for each row. And the idea of the competition was there was a model A and model B. So we had about like 66 different models like ChatGPT-4, ChatGPT 3.5, Llama, and others. And so to the pair of these models, model A, model B, a prompt was given. And then there was given a response by model A and model B. And then a human had to select which response was better. Like either it was model A or model B. And like according to the score he wanted to give to any of the model, it was either 0 or 1, or sometimes it might be two winners. So winner model A, winner model B. And that's why we have an additional row for winner tie, saying if they both won, it was 1. If they both didn't win, it was also 1. Or if there was like one winning model, it was 0. And having told that, we really had lots of data, and I think it's a decent amount of data. But we noticed that at the end, like more to the end of the competition, that many Kaggle teams who participated in this competition, they used lots of external data. And so, yeah.
And then how to assess the quality of their work. So it was simply based on the log loss, that the mathematical formula for this log loss is the summation of the true labels times the probabilities, the log of the probabilities related to that sample of that class. So, and then divided everything by n, that is a number of sample. So we sent this the results of our work to the Kaggle, and then Kaggle is providing us the score, and that score is the public score. That is criteria is that log loss, and the log loss is, if it's only by chance, it's 1.09, and that means that all of the labels is 0.33. But our goal is to improve our log loss to have a much less value than the chance value of 1.09.
Yeah, so when we started first with the competition, we realized that like we decided to start with one model, try this, try that, and just try to make the submission. But the problem was it wasn't so easy to actually submit your results. First of all, there are so many restrictions given by Kaggle for your submissions, like internet connection off, just all the things we're going to talk about later. But also, we had 5 submissions per day for the team. So if we submit a lot, seeing the score, sometimes it takes lots of time. For example, you just submit your code, then you're waiting for half an hour, sometimes like more, for 2-3 hours to see the score. Then you get the score, and you need to compare it to the leaderboard because you always want to perform better. And so I think the main idea for us was to understand when we are doing, like when we're implementing the model, we need to be sure that we are always really consistent with the leaderboard. So instead of doing submissions, like 5 submissions each day, we can like evaluate the accuracy of the function and just log loss, and to see how good we are without making the submissions each time.
The challenges we had in these competitions, it was a messy data, and we saw that we have multiple prompts and responses. And for example, one of the problems, it was about the example of the prompt that it's consisting of lots of prompts, and based on the questions that it was this. as we see it. So Anya is explaining more
Yeah,
about that.
so as an example of prompt here, you can see that it's a list of 2 prompts, and there might be a question, right? There might be multiple questions, or sometimes in some cases, you could see actually a kind of a chart of a user and a model like GPT, I don't know, whatever model you use. So you could see the question which is given as a prompt to a model, then you see the reply by a person. It's actually really the same when you're talking to ChatGPT and asking some questions. You can like ask another question to be more precise. You want to hear more about the specific things about what you've asked. So actually it was pretty messy to see all this kind of stuff because the prompts were not consistent. They could be any different. And the other problem we had is the limitations. And I think on the next slides, we're going to talk more about that. So first of all, we had a limitation on the inference notebook. It's limitations given by Kaggle. It's a CPU and GPU runtime. It's not more than 9 hours. So you should make sure that when you run your inference function for submission, it doesn't run longer than 9 hours. Also, for the training notebook, we just could use only 30 hours per week of GPU and 20 hours of TPU per week. And because of that, it just actually caused lots of troubles. Because when you're talking about large language models, sometimes it's about like not hours, but weeks of running, of training. And that's why we had to really stick with some model which is going to be within this bandwidth. And also our main idea was like we tried many models, which we're going to discuss later, but we end up using Llama 3.18b model. And so we stick to training using TPU to accelerate training. Also, for the data usage, we had to use only 50% of the data at once. So we actually trained on the whole data set, but during the training, it was first 50% and then the second 50% of a data set. And also tell about the sequence lengths. We started with 1024, went up to 2048, but we had to reduce to 1668 to be able to run that.
And in the next, you mentioned in the next.
Yes.
So the model selection that we use, it was about, we just simply use the, at the beginning, use the logistic regressions and decision tree. It was a base. And then after that, we started merging the models with each other, TF-IDF and Debersa and TF-IDF and like GBM, LGBM, and Llama 3 and TF-IDF. And also we connect to the API of OpenAI, ChatGPT, and we use when after all of this we ran into the problems that there was not enough improvements on the log loss. So that's the reason that we need a deeper understanding of the text knowledge. So that's the reason we went to the neural network and we applied Llama and Gemma and the combination together. So Anya is also talking more about how we connect to the ChatGPT, and it was a success.
Yeah, I also mentioned about logistics regression. It was the first model we've tried. I mean, we obviously were sure it wasn't going to work, but just when we compared the scores of the leaderboards to the logistic regressions output, so we think it was even nearly as good as a leaderboard. So it was like really high. Let's say the leaderboard score, the best score was about 102 that time, or maybe a little bit lower. For logistic regression, it was like way more than that, like 2.8, 2.5, something like that. And for OpenAI GPT, the idea, I think it was pretty interesting. So what we were trying to do is we wanted to actually to feed the prompts with the responses to the OpenAI using actually API, and to get an additional metrics. For example, just we made up 5 or more metrics saying, okay, ChatGPT, tell us how good was the response. Was this reliable? Was it true? And based on the metrics we're going to get from ChatGPT, we're going to like use this metric to evaluate the score and maybe to receive some additional information on how human could select the winning model. But it's appeared that for ChatGPT itself, especially for the free tier, it's going to have restrictions like three prompts per minute and 200 per day. And it's appeared without data for like 57,000. It was not nearly possible to do that.
Yeah, and also we try Google Gemini, and that was also, it was very costly, and we couldn't apply that. So hopefully in the next competitions, we are planning to go to the each models and go to the API of each of those other models in the Hugging Face and Almost, and then connect to those and create the extra column, extra features. And in that, we could improve the model's efficiencies and our predictions. So for example, for one of the methods that we use, it was a Llama 3 TF-IDF and like GBM that as we know that we just combine them and just combine them of the TF-IDF with the more precise methods of Llama that gives us the metrics of the embedding vectors and the TF-IDF vectors. And then we use the light GPM to gives us the precise dominant probabilities that which one is going to be a winner. So we also use that methods and it has a higher efficiency compared to others.
Yeah, so comparing all the models, we ended up with Llama 3 model 8B, and the main idea was for us to play with the parameters, so with fine-tuning. So we end up using LoRa with rank 4 and alpha 8, starting like we've tried many different learning rates, and it's appeared that 1 to the 8 minus 5 was the best one for us. And also we use a cosine schedule for learning rates. And actually, the thing is, the number of epochs we had to use, it was only 2. Actually, I think Ryan tried to run 4 and 5. 5 appeared that it was a lot overfitting, right? And 2 epochs, it seems like it was within the time restrictions we had. And even though we use TPU, which is actually tends to work with a higher batch sizes like 16, 32, 16 seemed to work best for us.
The architecture design of our models, it was a auto model for sequence classifications that we noticed that this one will provide us the probabilities, and instead of the LM sequences that it was only a hard labels, but this one will provide us the soft labels. And we also use the 8-bit quantization. The reason is when the number of bits is increasing, it's affecting on the memory efficiency. And we try a 4-bit quantization and 8-bit both together, and we noticed that the 8-bit quantizations is providing us the better score. So that's why we rely on that.
Yeah, so when the competition actually ended, we decided to look through all the write-ups, winners now. So for 5 top winning team, it just appeared that the common thing for all of them was using external data. So people really used a lot. And then for the first winning place, he actually combined most of the things was done for any other people. It was external data set, it was a knowledge distillation and test time augmentation. For the second play, there was a unique prompt design, and all of the teams used the ensemble. So just combination of the large models like Llama, Gemma, Cuban. And the first place actually appeared to work pretty well with a sequence length on 1024. So with the knowledge distillation, he just ended up with a really high score. But for the others team, we noticed that the max length was really high. It was even like higher than 3000. And all of the teams were managing with GPU memory issues. So,
one of the, as Anya mentioned, that they use all of those winners use the external data and pseudo labeling. So the pseudo labeling was simply the unlabeled data, and they generate this pseudo labelings through the diverse LLMs techniques that is just providing bunch of unlabeled data, and they train the pre-trained labelings on the trained data, and then they use that models to predict the labels of the pseudo labelings, and then they merge the pseudo labels and the original data together, or the external data, all of it merging together, and then they go to the fine tunings and other process of the optimizations. And also, we saw that in these competitions, they use the methods of the knowledge distillations that we were not aware of that. So we face the problems of the GPU and memory issues a lot, but we had no idea that we could use this. And we could just simply use the small language models and then use the application of larger language models to mimic that a smaller language. It can be like a student's learning from the teacher. So a student can mimic the behavior of the large language model. Our small language, for example, was a Llama 3 8B, 8 billion parameters that we use. And the teacher model was a 70 billion parameters that the winners use that technique that is used actually the 70 billion in the behavior of 8 billion. So in that part, a smaller language is just mimicking everything, and then it's providing the soft labels, because the teacher model is based on the some temperature parameters, is dividing and providing that probability, and when the student is mimicking, they provide that. So that providing the soft loss. And also the students model, like that small language models that we have, they also mimic the behavior of the trained data. So the original trained data. So how this happened is just mostly about the correctness. So they have the behavior of the teacher model, but also they have for the precise and correctness, they have a behavior of the trained data. And then based on this, as we see that they have a loss. They have a loss that it's the combination of the soft loss and the hard loss, that the hard loss is coming from the trained data and the soft loss is coming from the teacher model. So it was a very impressive part when we saw this, that how we struggle with these large language models when we could just simply easily use all of those smalls. And the beautiful part is about when we just using the hard labels, we just say that for this student and teacher, we just say, for example, dog or cat is binary, 1 or 0. But when we see the soft labels, they give the probability and they don't ignore the existence of others. They say that 80% is dog and 15% is cat and 5% is wolf. And how they give these probabilities is based on the similarities that they said that all of them, they have fur, and all of them, they have 4 legs. So we do not ignore the existence of other alternatives, but we also put everything into consideration. So that's something that we learn it in this techniques that those winners use, and we're hoping that we will apply this in for the future Kaggle competitions when we face the problem of GPU and memory issues.
Yeah, so the other technique is a test time augmentation. In particular, in this competition, the person used swapping on response A and response B. So instead of like, we saw the data frame, so there is a prompt, response A and response B, and like to make it more like to have the equal contribution to the result, to the final prediction, just simply swapped the response A and response B in some, yeah, for some rows. So nothing fancy about this technique.
And also we saw that the winners of these competitions, they use two different functions for the problems that we talk about it at the beginning, that we have different prompts with consisting of different questions. So they use the prompt response A and response B format in their function, and also prompt response A, prompt response B, that when one is ending, it goes to another response. So they enforce the data frame to behave in this format. And in that way, they cleanse the data.
Yeah, an ensemble of various models, which is used for by all the Kagglers. Especially Ryan, he just came up with this idea. We were trying to implement it using Llama and Gemma, but unfortunately, I think we were so much concentrated of the training of Llama models, so it's appeared like we didn't have time just to run both Llama and Gemma and to submit. We were really trying at the last day, but I think we just ended up not submitting this result because we've never just received the final prediction. So for all the winners for this competition and for the first place, he just trained the Cuban, Llama, and Gemma. And so then he just averaged the results, and it's appeared like for a second slide. We also performed QLoRa, and we performed just LoRa for Llama 3 model, and just this guy who won the competition, he used LoRa for Gemma and QLoRa for both Llama and no, I think he used LoRa for Gemma and QLoRa for Llama and Cuban, and then the combination of all that. And I think the rank was pretty much higher than we had, right? And so just the alpha parameters were much higher.
And what we learned also about the GPU memory issues, it was in addition to the knowledge distillations that we talk about it, those winners, they also use some techniques like flash attentions and logic soft capping and model pipelining. So the idea for the flash attention was to simply reduce the redundant competitions in transformers like BERT or GPT. And we were unaware about it. So they also use the logic soft. And the idea for this is they wanted to provide a threshold, so that threshold can prevent the high probabilities that is given to the particular class or tokens. So sometimes the probability to that logic can be very too high or it can be too low. So when they assign a threshold, it can reduce all of those redundant competitions using the back propagations. And they also use the model pipelining. And the idea was it breaks the model into the different smaller segments, and that can be processed on the different GPU. Because there's no GPU limitations on the training of the Kaggles. And that way that longer models, they can be like large language models, they can be processed, and that will also help to reduce the training time. And in a summary of whatever we did and whatever we are hoping to accomplish in the future is we will be planning to do a multiple small language models that they are mimicking the behavior of the large language models, 20 plus models. And then in addition to that, based on the nature of the data, we also planning to minimize the cleaning part, because we may spend a very long time on the cleaning, but we could just go to the language models and instead of focusing that much to the cleaning sections that the winners of this competition didn't do that much. And also after we apply all of those language models, we could select the top models and we assemble and merge them together based on the based on how they are important they are, and give them a different participations, if they are equally distributed or if they have a distributions are different. And that way we could achieve the best results. And as we also talk about knowledge distillation, that is very important. And we are also planning to use the flash attentions and logic softcap and pipelining, all of them together, that in that way we could improve the memory efficiency and stabilities of the models during the inference and training, that all of the majority of our issues that we were not able to run it on the Kaggle based on that limitations can be resolved by applying these techniques in the future. But we also, before that, we also giving this advice that it's not always going to the Kaggle's competitions. We could also do the Kaggle's knowledge, because the problem is sometimes when we try to submit our results to the Kaggle, we see that there is a limitations that even it could not even run one signature, one sections of our work. Even not parts of our work would be processed. So that's the reason we would advise that also get the information about the knowledge part instead of just going to the competitions.
Yeah, and as a conclusion, I would say that I was coming from machine learning field, so I've never done anything with AI, LLMs, and it was a great opportunity for me to start and to break into this field. And thanks to, again, Ted and Ryan for doing that for us, and just it's like really invaluable. And I would say that for the 3 months, I just gained so much knowledge about that, just read a lot. I don't know, like, for the last years, spending so much money on Coursera courses, on boot camps and everything, I would say that this competition gave me much more than all of them all together. And it's completely free, so you can participate, you can find any information. There are so many people who really love to share the knowledge, and you can ask any questions. And I think people are really willing to be really helpful and to answer all of them. So I would say, just if you're hesitant about like going to the competition, it's not necessarily needs to be like you go, you win. No, you just participate, you gain lots of knowledge and all the stuff you've never done before. So it's not painful, you just try doing that. The first thing which was hard to us probably is to understand how submission works and how actually Kaggle is very specific. But I think it just, well, unless you don't know, it's hard. But when you learn how to do that, it's like a smooth process of learning and just gaining your knowledge every day. So, yeah.
And also, I wanted to mention that you really don't need to put it to run everything on the Kaggle environment. You can just easily start it with the small language models instead of large language models and run it on your own CPU, even if your computer doesn't have GPU. So in that way, you could just make yourself more familiar with the variety of models and also do fine tuning and get the results and then compare the results with each other, and instead of going straightly to the large language models. Yep.
I think that's all.
I think we'll open it up for a few questions, either in the room or online.
I can jump in if you don't mind.
Yeah, that's someone.
Can you hear me?
I have a question about the text. Slide 3, we're talking about their non-text things that were causing problems. Meaning like quotes and question marks or character terms or.
Yeah.
We can repeat the question for people here.
Yeah. So the question is about the prompt, right? So when you had a prompt on
Yeah, you're saying there were 3 items that were there. And that's the
yes.
Lots of non-text signs and text.
Yeah, so there might be things like, okay, there is like the word test, right? So just testing, how could you actually choose a winner when you have this prompt saying test, right? But sometimes really there were so funny answers by different models. So the winner was chosen sometimes based on even these words, or there might be just question marks, or there might be, I don't know, different types of even non-text things like, I don't know what, digits, right, whatever. But it's appeared that the cleaning actually all this kind of text didn't help a lot. It's really didn't improve. It's, I think, made us harder to choose the winner. So I think it's really, you know, when you come to the real world challenge, you know that you have to start with data cleaning. And this competition seems like you shouldn't do that actually, because you gain so much information out of all this messy stuff. Yeah, that was surprising.
Georgia.
All right, so there.
I have my microphone. Just let George know.
I can
Yes.
ask a question if you don't mind.
You should unmute him.
You. Chat, right?
No.
Hi, George. Go ahead with your question.
Oh, thank you. Can you hear me?
Isn't this question?
Awesome.
Do you have
So,
sound on?
Maybe.
so the question,
Up here.
let me know if you can hear me.
Yeah, we can
Yes,
hear
we
you.
can.
Thank you so much. I appreciate it. Great presentation. Really, really good. So my question is regarding the scope and the end goal of the competition. It's a really useful competition. So you have basically large language models and you're trying to understand how the human labelers or the human judges are responding, correct? So the goal is to understand a little bit better how a large language model can be better aligned with human preferences. So given that you're trying to understand how an LLM works, and in your framework, you're also using LLMs, is there any idea or notion of explainability? Like how are the competition organizers maybe going to use this data and try to understand how large language models better align? I just had like a larger question regarding the competition itself, not the approach.
Yeah, got it. It's a great question, actually. Right, so instead of understanding from your knowledge how a human chooses the winner, you're trying like a large language model to understand how
Yeah.
the winner goes,
Yeah,
right?
you're studying a phenomena, but you use tools that use the phenomena to understand the phenomena. So it's like a circular logic to me. So I'm just trying to understand how all that's useful.
That's true. That's why just I think we've used different approaches because it seemed like maybe the neural networks could have helped with that, but it's at the end it's appeared that only large language model could catch this difference. And since the I think it's trained for that, right? That's why just it's really capable of this stuff, like to understand how based on which metrics actually the human selected which model, which is yeah, interesting. It's kind of phenomenon.
That's why we use like a 20 or maybe more models to find out that which one corresponding the best. Then use the ensembling.
Any other questions before we switch to the next presentation?
So, did you check the distribution of this models between data for large language models, where the data itself was in a bias towards I don't know what were the computations they had.
Yeah, you mean responses and prompts? Yeah.
Sort of like kind of Bayesian trial, like
Yeah.
response is biased.
Right. So the question is about the bias for the distribution of responses. So we actually Chapman was 50-50, right? So in the beginning when we do this EDA, it's appeared like it was selected pretty uniformly. So we ended up used one of them, just Llama.
No,
Oh.
it's just in the data set.
Oh, in data set, 66 large language models. Yeah.
But it was not in the.
It was not in the task, right? We didn't know, like in the task, we could only see the prompt and the responses. but we've never seen what models were used. Yeah.
And for being not biased, we also changed the responses section. So we swap both of them. So, and then we get the average of swapping and not swapping in the way that they're equally distributed to generalize our data, not to be biased in one response more than another.
All right, thanks, guys. Thanks so much for sharing about this. Cool competition, and really glad to hear about your work and all the different tricks that people use with these LLMs.
Thank you.
All right, hold on for a sec, guys. We're gonna switch speakers, so give us just a minute to do the logistics.
All right. Hello, everyone. So I'll follow them up with a talk on TextGrad. So I've been doing a bunch of work with LMs, and this is something that I just kind of came across the last week, and I've been playing with it. And so I wanted to present on this because this was what I was already looking at.
You want to do your camera?
Sure. So just quick overview of TextGrad. So the main idea here is we have neural networks, and then normally we train them with backprop and gradient descent, and we look at the actual weights, and then we're able to make changes to the weights in order to optimize them to do a certain thing. But with a lot of these large language models, we don't actually have access directly to the weights, or we want to just optimize them through prompting. And so that's an easier way for us to get better behavior out of them. So the inputs to a large language model we can change. And so we can just say, if we just ask a better question or we give it better directions, we'll get a better response back. And so there's this whole area of prompt engineering that people have been just kind of like, there's people who professionally like ask questions of these models, but it's hard to define, are we actually doing things the best that they possibly can? And so various systems have been made for optimizing these automatically. And so this is one of those systems basically saying, instead of having a human prompt engineer, what if you had a large language model that was in the loop saying basically, okay, regenerate the question, try various different combinations and see if you can find a prompt that gets you more of what you want. And so what this does is a sort of play on PyTorch, where PyTorch kind of wraps the neural network and then says, here's the optimizer and here's how we change the weights. TextGrad is trying to do the same thing, but for text-based responses where you can't do the same numerical optimization. So I'll walk us through how this works. So over here, we have normal neural network. We have the weights and biases, and you can do the loss function and then backprop through the whole thing, and you have your gradients. and that's all fine. We train neural networks like that all the time. But then now we have a more complex pipeline where an LLM is just a piece of this whole puzzle. And then on top of that, we have prompts and we have responses and we have external inputs into the model. And so we can view this as sort of a graph again, like a neural network graph, and then say like we have this whole thing, and then optimize this one specific piece in order to get the behavior that you want. And so they, in all of their documentation and stuff, they have this analogy of like, okay, here's what it is in PyTorch, here's what it is in TextGrad. And so the whole point of it is basically saying, we can build out a whole graph of all of these things that are going into the large language model. Here's the layers of the pipeline. And then we can say, we want to optimize this specific prompt, or we want to optimize this answer. And so in a way, you're kind of doing like partial derivative of this little piece of the network. You're saying, what if I change something here, how is that going to change the rest of the things in the system? And so it was a little bit confusing to me at first what they meant by text gradients, and we'll look at some examples of that. So this text gradient, basically all it is just injecting the LLM as sort of an optimizer in there. So you say, here's a conversation with an LLM, here's the input, here's the output, and then you say, LLM, give us some feedback. Is that the correct response that you want? And that feedback becomes your gradient. And then with that gradient, you can say, okay, it did something wrong because XYZ. You have access to this prompt and you can control this. What do we change in this part of the prompt or pipeline in order to get more of the behavior that you want? And so this gradient is really just text feedback. It's not a number. It can be any string, basically. It can just be, hey, your response was too brief. You need to make responses that are more verbose. Or your response was incorrect because XYZ. Anything that an LLM can judge. It can look at it and it can say, this is correct, this is incorrect. And then how do we actually optimize with that gradient? So we have our little bit of feedback, and then we say, here's the prompt that I want to optimize. And you can have another layer of the LLM saying basically, here's our prompt, here's the feedback that was given. How do I alter this prompt in order to get that feedback to be rectified? And so this whole TextGrad system, it seems kind of simple to basically be like, okay, feedback, go correct yourself. But the TextGrad system is kind of nice because you can do it in a bigger pipeline and understand this goes into that, and so it can be multiple layers deep and say, I only want to optimize this one specific thing, and it understands all of the different layers of that and can kind of layer on the context that you need. So it can be something like in this previous slide, where it's like, here's an LLM, we give it a prompt, but then on top of that, that output is going into another LLM, and that is also getting some search engine results, so it's got some extra context. And so you build out this whole graph, and then you basically say, here's all of the inputs and outputs of that, give it to the LLM, do some feedback, and then fix the part that you're actually trying to optimize. And so the kind of process of saying give feedback and optimize is generic enough that you can do that on your own. That's easy to do with an LLM, but this more like complicated, I'm going to build a whole graph and then do auto differentiation on it kind of is the part that's interesting with TextGrad, because it's more generalized. You can just say, here's my whole pipeline, build up all this stuff, and then say, alter that one piece. So you can use it to optimize RAG and all kinds of other things that have more complex workflows. So here's an example of one of the problems that they were solving. So it's leak code problem. So it's just, let's solve this specific coding problem. And what they can do with it is they can basically say, okay, here's the input prompt, and then here's the response, and then evaluate that response, and then have the test results of actually running the code, and do that multiple times, and just run this feedback loop and say, okay, is the answer correct? Is the answer wrong? And say, run this multiple times and see if it actually gets the correct result. So this 0 shot down here is basically just giving it the coding problem and saying, solve this. And then it gets it right 26% of the time. And then there's this other reflection technique, which is just kind of a certain prompting trick saying basically, think about this before and then show your work. And then after that, give your response. And TextGrad is different in that you can do multiple loops of that, saying, here's my answer, here's the feedback, here's my answer, here's the feedback, and keep doing that multiple times. And then they were showing that you're able to get up to 36% from that. So people are fighting heavily for these accuracy gains, where it's like the difference between 26% and 28% is people saying, oh, wow, Claude is amazing right now, or GPT-4o is the best. And then you can get a 10% gain off of just basically saying like, prompt it in this certain way or use this workflow. So it's pretty incredible that you can just say like, okay, now just do 5 passes of this thing and you'll get much better results. Whereas someone else like OpenAI is saying, we're going to spend $1 billion training this model. So if you just know the correct way to operate things and prompt it, you can get better results. So here's kind of a code example of what this looks like. So we have this test data set, and we have a question, we have an answer, and then we have a loss function. And all that this loss function is doing is basically looking at the response and saying, is this correct, A, B, C, D? And returning back a string saying, actually, you're wrong because of X, Y, Z. It was actually C, and here's the reason why. And so it gives it some feedback on what exactly the incorrect choice or correct choice was. And so they've got this textual gradient descent, and it's saying, in this context, we want to optimize the solution. So it's going to do multiple passes of try to make a guess, and then measure its feedback, and then after that, try to do some optimization in order to get the correct response in the end. So that's one way of solving things. So you can plug in basically whatever you want into this parameter. So anything in your graph, you can say, optimize this now. So one way is just directly saying, I'm going to do 5 loops on this individual problem and see if just kind of giving feedback to myself, I can come to a better solution. But another way of doing this is prompt optimization. So this is the one that I've been mostly playing with. And the idea here is you have some data and you have inputs and expected outputs, and then you want to optimize your prompt in order to get closer to that expected output. So all you're doing is you're saying modify this prompt until you get the behavior out that you want, basically. So this is what it looks like. So you have a model and you give it some initial system prompt, and what you're doing here is you're looping over the data and you're saying, make a response, judge how good that response was, and then give feedback on that. And then that's kind of your loss that you're returning. So let's say you did predictions for 4 different documents in, and you expected to get a certain result out. And then you concatenate sort of like an accuracy report saying like, did it do the right thing for this one? Did it do the right thing for that one? And then you concatenate all of those together. And then when it does the backwards pass, it's taking that back to the prompt and saying, given these 4 pieces of feedback, how do I change the prompt in order to make it do more of what I want? So here's some of the results for that, for the actual prompt optimization. So they were comparing with GPT-4o, and they're using actually 3.5, and they're using 4o as the optimizer. And so that's one of the interesting tricks that you can do, is you can say, here's the large language model that I'm actually going to deploy with, but I'm going to use an even smarter one as sort of the judge in order to teach the other one and guide the other one in terms of the prompting. So this here is chain of thought. And so this is sort of a certain way of prompting the model and getting it to behave. And this is kind of accepted to be a good starting place for your prompting. And so they're saying, here's what happens if you just give it a decent prompt to start. And then this DSPy is another system that's basically saying there's ways that you can pack in examples of the inputs and outputs that you want, and DSPy helps you plug those in. So if you have some data and you say, here's 8 examples of the way that I want you to reply, that's your prompt now, saying basically, here's your 8 inputs, here's your 8 outputs, I expect you to do this, and then the model's able to try to follow the label data as instructions. And then they show that the TextGrad can even beat that accuracy without having explicitly injected that into the prompt. So just giving it the best directions, it can actually get even higher accuracy than if you just directly said, here's the input, here's the expected output, and then here's some new data to plug in. So the TextGrad is pretty powerful in that it can construct a strong prompt for you over time. So here's what this might look like. So here's what a starting prompt might be. They say like, okay, here's the prompt in order to solve this problem. And then you do multiple iterations of this, and it's changing the prompt using the feedback that it was given. And then eventually you get something like this. And so you gain several percentage points just from running this system for, in this case, they only ran it for 12 iterations, and it was able to get something that was several percent better. So you could do this in under an hour, and all of a sudden you get this decent gain. So I'll pause for questions, and then I'll go show some of the code that I've actually been using. Any questions in here? Yeah.
Okay, so there's the judge that you keep 4.0. They use some additional models, or
they only used 4.0. So the model that is doing the majority of the work is 3.5, and then they had 4.0 as the judge of the quality and giving the feedback.
Okay, I was just asking, I was curious, like taking different results with using different models for the judge, and maybe how did they account for the quality of the judge affecting the entire system versus the framework that they proposed, right? If we don't know if like, okay, maybe it's generating better responses because of this, really powerful model, or is it due to the whole framework that they developed? So I'm curious how they.
Yeah, so the tasks that they showed, there's known like numerical values. It's multiple choice or it's counting. So they were able to numerically evaluate, is this correct? Is this incorrect? And so it's not necessarily GPT 4.0 saying this is good, this is bad. That's just the feedback inside of the system. So the metrics are constant, but the feedback could be changed out. But in the paper, they didn't try any other model. So they didn't have Claude or anything else. So it's hard to say exactly what was the deciding factor there.
Question about prompt generator? I don't know that. I don't do that.
The prompt generator, in my understanding, it's kind of one layer simpler than that. The prompt generator is basically saying, here, do another LLM pass and try to generate me a better prompt. So it's just a single, like, here's my starting prompt, try to flesh it out more, try to rephrase it, or try to do something better. But it's not the same as TextGrad, because TextGrad is trying to map the whole pipeline and saying, okay, all of this in context, how do you optimize this? That's the big difference with TextGrad, is it's kind of a generalization saying that we can handle even bigger than that. Yeah.
I would assume it's kind of depends on what the LLM is actually trained with, and its accuracy and its output. So if it's something that was in the original training set, you potentially could get enough out of it. But if it's something that it wasn't trained with, ultimately, no matter how you engineer the prompts, I would assume it would actually not get better and maybe okay.
Yeah.
Is that true?
Yeah, I mean, there's definitely scenarios where you're not going to teach a model anything within this prompt. But if it is something that it's capable of doing, you can get gains out of just asking it the right question. So the big use for this is I have it and it's doing 40% accuracy. And I know that if I just ask it a different question, I can get 57% accuracy, for example. That's what I'll show that in a second, but that's what I've done on my own use case is basically my company has been benchmarking some of these different models, and we've said, here, use this prompt in order to see how good we are at this certain thing. And then I just plug this in, and it's like, actually, this model that we thought was 40% is actually doing 57% now. And so it's like that completely changes our leaderboard of how these different models are doing. And it's like, well, we just asked it a different question and we gave it some better directions. And so it's useful to understand like how far can you actually push these models. In reality, we've seen that you're not going to make Llama 8B beat GPT-4o, but you're going to get significantly more bang for your buck. But it depends. Like the scenario you're saying, like if 8B is just not smart enough to do the thing, it's just going to fail, and you might just need 4o in order to have any chance of doing it successfully.
The transformer layer as well. Helping it understand what actually talk about or what they respond to.
Yeah.
So it's not necessarily able to say, but it's passing through to understand what it's passing through.
Yeah.
George,
Yeah. Also, go ahead.
Can I ask a question?
Should I turn my audio up, or is it playing through the?
It'll be on your audio.
Okay.
Okay, let me know if you can hear me. 1, 2, 3.
Yeah, there you go.
Perfect. Thank you, Ryan. Great tool and great similarity with PyTorch. Just some clarification questions. So this reminds me a little of the data-centric approach in AI. So you're fixing your model and you're trying to just maybe play with the prompt or the input data here and try to get a better value out of it. So these percentages that you mentioned, this improvement, are they generated by the LLM itself? So the LLM is telling you that my output quality is 40% good or 50% good, or do you have like independent rating methods?
You have independent numerical scoring. So like one of the benchmarks that they used, it's the code one, like they know the code correctly ran or it didn't. So they can directly judge, did they solve the problem or not? And then another one is counting. So it's basically like the set of problems is like, I have 3 apples and 4 bananas and 1 pencil. How many objects do I have? And so it's directly they can say, okay, here's the actual integer answer, and then did it get it correct or not? So the actual scoring that they're doing is not based on LLM judge. It's just the feedback that helps it iterate is the LLM.
Got it. That's awesome. Okay, so then the goal is to just find a better prompt to come to that desired outcome.
Yeah.
And the prompt could be text. You also showed an example of code, so it can also be code, I guess.
Yeah. Yeah.
Got it. Thank you. Thank you so much.
Yeah.
Hey, Ryan.
Yeah.
Comment. I don't know if you want to get into this, but like prompt tuning, you can actually improve the prompt over a data set, example data set, by just using gradient descent. But they show examples in the paper where they're like designing a drug and the intermediates are not differentiable whatsoever. So that's the case where you really need the LLM to judge.
Yeah. Yeah. So I will hop over to some code. So this is something that I've been playing with at work. So Ted mentioning prompt tuning, one of the techniques that I use a lot at work that I've kind of been evangelizing at my company is prompt tuning, which is this trick where you can say, I'm going to directly do gradient descent, but the thing that I'm optimizing isn't the neural network, it's the embeddings that go into the model. And so that's kind of a way of saying, like, instead of engineering a prompt, I'm going to engineer a vector that goes into the model, and then that is like an optimized vector for my given use case. So if I have a known set of 100 inputs and outputs, then I can actually do gradient descent if I have access to the model, but not actually modify the model itself. And so I kind of have treated that as like, this is probably the upper bound of what you can do with a prompt because it's directly optimizing it. But this is kind of saying, what can I do with just optimizing the text instead of the embedding? And so I'm trying to compare, like, is prompt tuning always actually better than just giving it different variations of text? And so that's what I've been playing with. So what I did is I went and I took one of their example notebooks and I just modified it with my own data set in and also doing my own feedback. So they had some stuff that was pre-coded for the object counting problem. So it's the one that I was just describing where it's like I have 1 apple and 4 bananas, and then so I just kind of gutted their stuff out and said, I'm going to plug my own data and my own judgment of the results and then see if this system is able to work on the same stuff. And so what I had to do was basically build out my evaluation piece. So originally their thing was just about that counting result. But in my work, I've done stuff with invoices. And so we have this function that basically says, take this JSON, compare it to our expected JSON, and then output a report saying how accurate was the model at doing this thing. And so I can show one of these down here. So we pass it through the model and then we get back this report saying like, okay, you did the billing address wrong, you did the billing name wrong, you got the invoice date correct. And so this is what I've actually been using as feedback to the model. So I say, model, you got this document as input. I want you to extract some JSON out as the output. And then I'm going to give you the feedback of this table saying how you did. And so this table directly is what I've been giving to the model saying, here's how you did. And then the prompt that we've been using is this, and it's actually something that we got from GPT-4. And we basically said, so this is what we give to a model. So this is saying you're an invoice extractor, follow these directions. We want you to output JSON in this format. And so this is actually a pretty optimized prompt. It gives good directions, tells you about all of the fields, says, hey, when you're looking at this, do the date in this format and stuff like that. And so it's a pretty strong prompt on its own. But what we found is using this prompt optimization thing, we give it the feedback, we let it iterate for a little bit. It goes from 40% to 57% for Llama 3 8B, which is pretty surprising because that puts it up a weight class in terms of model. And it nearly approaches what we can do with prompt tuning. Prompt tuning is still a little bit better, but only like 2% or something like that. So it's interesting that just by asking it the right question, you can get such a big change in result. And the input to this is an invoice that looks like
a PDF and you're doing the OCR against it, and then it's really there. Okay.
Yeah. So it would be something like this, and then I have, so it looks like this. So we do the OCR text, we get this result back, and then here's an example of what we would expect the response to be. And so
Failure getting the date could be OCR right there.
Yeah.
Okay.
Yeah. Yeah.
Well,
Absolutely.
probably using OCR.
Yeah. And so I have way too much output. But I printed out through this process, every time it's trying things, I print out the new best prompt that it outputs. So you can see that it started at like 39%. And even on its first try, it got it up to 43%. And so it rewrote the prompt as this. And so it gave, it's kind of interesting. It's saying use named entity recognition, use regular expressions, use fuzzy matching, even though an LLM doesn't have those capabilities, just asking it to operate in that way for some reason gets it slightly better accuracy. And so you can see it added all of these additional tips, and just doing that, it was able to get 3% better on its first step. And then it continues going and it gets slightly better. And so this one I only ran for 4 steps. But on top of that, we can see like one of the things that I defined is like, here's what all of these things mean, and then here's the feedback report, and then it's able to look at that in conjunction with the input and the output, and then rewrite the prompt iteratively in order to get better results out of that.
By the way, just a quick comment. Sorry, you might have to repeat this for the
Yeah.
online people. But if I remember right, it's concatenating the old prompt and the new prompt generated. So even if it generated a bad prompt that got worse performance, it's able to sort of remember that that direction was unhelpful and go in a different direction. It's not just saying like, oh, try this, and then, oh, try that, like you, it's more like remembering the sequence. And so then that's where it's more like following a gradient, because you can see what's a bad direction, what's a good direction, you need to go, you know, the uphill direction.
Yeah.
This as a feedback to model selection. Meaning when your prompts are, you're only getting so much gain out of it, but if you then go rebuild the recognitions out of it, so we'll train it specifically saying invoice data is only going to be from 1900 to 2024. In the future, it's going to be in the past. So if you see anything like this, the probability that it's wrong, and either identify that it's wrong, and or make a guess what it's supposed to be. You know, there's no 13th month, so it's probably 12, 11, or 10 because it's 2 digits. And having that mechanism function.
Yeah, I mean that's definitely that's part of what this is trying to do. So like in the prompt itself, if we look up here, like that's what it's trying to do, is it's realizing like, oh, this time you returned it in this way and that was wrong. So now I'm going to add something to the prompt in order to give you that additional guidance on, here are your list of possible months, here are the list of, you don't expect a $sign to be in the invoice number, for example. And so it's adding all of those things potentially as it learns them, which is interesting to do. And I have another variation where I was trying to make it directly inject the few shot example. So like the DSPy one, what it's doing is saying, here's 8 example inputs, here's 8 example outputs. And so just prompting this slightly differently, I can say like, hey, try to use examples as part of your prompt in order to, and it can start building out like, oh, this is a useful example to have because it's some weird case. So it should be part of the prompt in order to get the response that you want when that weird side case happens.
My question is a little bit more in the next layer down, in the sense of if you could run it against, let's say, 4 different versions of an agent or 4 different versions of a RAG, and it's sitting on top of the LLM. ChatGPT 4 is never changed. But the way that you're bringing that data in, the way you're understanding it and saying, hey, look, this is out of bounds, I'm not going to send it to the LLM, it's not going to, doesn't matter. Doing like maybe testing from that perspective, or testing versions of it to figure out what is the most optimal back end to process this. Well, the prompt going to get you so far, but really it's disabled by the inaccuracy of the OCR engines. So we have 5 different OCR engines that back end is tweaked in several different ways. Then you can use it as a selection of, this is the simplest prompt with the highest outcome.
Yeah.
The highest accuracy.
Yeah.
So you can constantly get it and start pushing towards that, let's say a 95% confidence that you would need for it to do billing for an organization.
I mean, it's difficult to do. Part of the ambition of the TextGrad is to be like, let's optimize the whole pipeline, but there's certain things that you can't really control, like the quality of the OCR. You might not be able to really give feedback to it, but you might have something where you say, I have 5 different options. and run all of them, and then have the LLM choose which one it likes best. And then maybe you could do something with TextGrad and that, saying like, have an LLM that sits and then judges and says, this one looks unreasonable because of the stuff that you were talking about, where it's like, it can't be a future date, it can't be something else like that.
Okay, but also something you parent, you don't need to keep it. You just literally fashion.
Yeah, and that's kind of the idea is, let's spend less focus, and if it's an issue, let's just flag it, or say if it says 0, it's supposed to be a 1, and it's a 99% probability that it's a 1, it's like a 1 and it's respond. So you don't have to figure out how to make the prompt more accurate. It's ultimately humans who consider people doing it, so LLMs are great because humans interface with it easily, and you want to make it very simple. First question you ask, your probability of answering your question versus I have to ask the question 15 times, and then suddenly I have to learn how to use the system.
Yeah.
It's interesting. Okay.
So in the chat, there's a question about cost effective efficiency. I don't know compared to what. And then similar type of question George asked about vision. And then actually vision's pretty cheap. I think.
So they actually have an example with multimodal LLMs. I haven't specifically played with that side of things, so I can't speak to that. But it's just with this, it's just the cost of a forward pass. So it's just the cost of whatever the model is. So if it's Llama 8B, if it's Llama 70B, if it's some vision model, whatever the cost is of generation, text generation, that's the fixed cost. So you're just doing a bunch of generation. So like with this, I've been able to get 40 tokens per second, and then that's just the speed of optimization for me. So whatever my generation length is divided by 40, that's how quickly I can iterate and do steps. And so if a vision model is doing the same thing, then it's whatever its speed is basically.
And Ryan, can I ask a clarification question? Your OCR system, is it highly accurate? You're sure that the extraction of data is done, fully, properly?
The OCR isn't perfect, and we know that, but we know that it's not the bottleneck with this necessarily, because we passed the same thing through GPT-4o, and we've seen results in the 80s or almost 90s. And so we know that if just giving GPT-4o the text, it can get 90% accuracy, then the limiting factor here is the LLM. It's not the OCR necessarily.
Okay, thank you.
Are prompts ever when optimized shorter, or they always longer?
They can be shorter. So that's one of the things that they showed, is actually you can say like part of your feedback can always be make this more concise, and then it will try to condense things. And so that is one of the feedback loops that you can do. Instead of saying optimize for accuracy, say optimize for conciseness, and then say save me tokens. Yeah.
For accuracy.
Yeah.
Yeah. Okay.
It's completely, I mean, I can show the prompts that I have here. Like it's truly just text. It's whatever I tell it to do. I can't guarantee that it's going to do it amazingly, but I just give it some definition of what optimal is, and then it will try to adjust for that. All right. Thank you, everyone.
Thanks, Ryan.
Thanks for that.